Ever wondered how a remote employee in another country can securely reach files sitting on a server back at headquarters? Welcome to Lesson 45 of our networking journey, VPN Fundamentals. Over the next few slides, we'll unpack how virtual private networks build encrypted tunnels across the untrusted internet, connecting entire sites or individual users as if they were sitting right on the corporate LAN. Let's get into it. Here's the roadmap for our time together. We'll start with the core problem VPNs were built to solve and demystify how tunneling actually moves your packets across hostile networks. From there, we'll contrast the two big deployment models, site to site for connecting offices and remote access for individual users. Then we'll compare the heavyweights, IPsec, SSL, TLS VPNs, and the newer WireGuard. And we'll close on a practical design decision every architect faces, split tunnel versus full tunnel. So let's start with the core problem. Before VPNs, if you wanted to connect a branch office to headquarters, you paid serious money for leased lines, MPLS circuits, T1s, dedicated fiber. The internet was sitting right there, cheap and everywhere, but it's fundamentally untrusted. Anyone along the path can sniff your traffic, and plain HTTPS, SMB, or SQL will leak credentials in seconds. VPNs flip that equation by wrapping your traffic in an encrypted tunnel, giving you confidentiality, integrity, and mutual authentication, essentially turning the cheap public internet into a private extension of your LAN. So how does that encrypted tunnel actually look on the wire? Your original packet with its private inner IP, its TCP or UDP header, and the application data, gets treated as pure payload. The VPN encrypts that whole thing and wraps it in a brand new packet with a public outer IP and a VPN header on top. The result is that routers across the internet only see traffic flowing between two public endpoints carrying an opaque encrypted blob. They can't tell if it's SSH, a database query, or a video call, and the internal 10. or 192.168 addresses never leak. Now let's see where that encryption actually lives, starting with the first major VPN flavor, site to site. Picture a branch office on 1020.0.24 needing to reach headquarters on 10.10.24. Instead of every employee launching a VPN client, the branch firewall and the HQ firewall hold a permanent tunnel between them, typically IPsec, sometimes GRE over IPsec, authenticated with a pre-shared key or certificates. Users on either side just send traffic to the other subnet as if it were local. The routers handle all the encryption silently in the background. The second flavor flips that model around. Remote access VPN, where the user, not the site, initiates the tunnel. Think of your laptop at home, your phone in a cafe, or a tablet from a hotel room. Each one runs client software like AnyConnect, OpenVPN, or a WireGuard app, and the user clicks connect, authenticates with username, password, and an MFA prompt, usually backed by Radius or SAML, and an on-demand encrypted tunnel comes up to the VPN gateway, also called the concentrator, at headquarters. From there, they reach the internal LAN as if they were sitting at a desk in the office. The protocols you'll see in the wild are SSL, TLS VPN, IPsec with IKEv2, and increasingly WireGuard for its speed and simplicity. Those protocols deserve a closer look because each one represents a different era of thinking about secure tunnels. IPsec, dating back to 1995, operates at layer 3 and is the workhorse, mature, hardware accelerated, brilliant for site to site, but notoriously painful to configure and famously allergic to NAT, which is why we invented NAT-T as a workaround. SSL TLS VPN came along in 2001 and solved the firewall problem elegantly by writing over TCP 443, the same port your browser uses. So it sails through hotel Wi-Fi and corporate proxies at the cost of some speed due to TCP in TCP. And then WireGuard, the new kid from 2018, throws out the complexity entirely. Roughly 4,000 lines of code versus 100,000 plus modern Cha-Cha 20 crypto, and key management so simple it fits on a sticky note which is why projects like Tailscale built whole mesh VPN ecosystems on top of it. Now here's a design decision every VPN deployment has to make. When the tunnel is up and a user opens YouTube, does that traffic ride the VPN or not? Split Tunnel says no. Only corporate destinations get encrypted to HQ, while Netflix and Spotify go straight out the local connection. That's fast and bandwidth friendly, but it means corporate security tools never see that web traffic, and a malware-infected laptop becomes a direct bridge into your network. Full Tunnel flips it. Everything goes through HQ, so your DNS filtering, web proxies, and DLP inspect every packet at the cost of hairpinning Zoom calls halfway across the country. Home users typically get split. Regulated industries like finance and healthcare almost always run full. Now, let's pop the hood on the cryptography itself. Every VPN, regardless of vendor, builds on the same four primitives. Symmetric ciphers like AES-256 or ChaCha20 do the heavy lifting. They're fast enough to encrypt bulk traffic at line rate. Asymmetric crypto, RSA, or the elliptic curve variants, is slow but solves the chicken and egg problem of how two strangers agree on a key over the open internet. Diffie-Hellman handles that exchange, and HMAC stamped each packet so tampering is detectable. The real magic, though, is perfect forward secrecy. Ephemeral DH keys per session mean that even if an attacker steals your long-term private key tomorrow, yesterday's captured traffic stays unreadable. Modern stacks, IKEV2, WireGuard, TLS 1.3 give you PFS out of the box. With the crypto foundations in place, every real-world VPN rollout comes down to 5 recurring design questions. First, are you connecting sites or users? Because site-to-site and remote access often share a box but need very different configs. Second, which protocol fits? ITSEC is the workhorse for site-to-site. SSL TLS punches through restrictive networks, and WireGuard is increasingly the default for greenfield builds. Third, split tunnel or full tunnel. Pure performance and user experience on one side, security and visibility on the other. Fourth, pre-shared keys versus certificates. PSKs are quick to set up but painful to rotate, while certs scale and let you revoke individual devices. And fifth, MFA, non-negotiable today, because a stolen password without it hands an attacker your entire corporate network. Now, with those design questions settled, let's talk about where deployments actually go wrong, because these 5 pitfalls show up again and again in the field. Overlapping IP subnets is the classic. Both sides use 192.168.1.0.24. The tunnel comes up green, but nothing routes. So plan your addressing early with a unique octet per site. A single pre-shared key shared across everything means one leak compromises the whole estate, so move to certificates for site-to-site and per-user credentials for remote access. Skipping MFA turns a phished password into full network access, and trusting the tunnel as if it were the user is how a compromised laptop becomes lateral movement. Assume zero trust and authorize every resource. And finally, don't forget MTU. Tunnel overhead breaks large packets, so clamp MSS on the interface, typically around 1360 for IPsec. So let's pull the whole picture together. At its core, a VPN is just an encrypted tunnel, your original packet wrapped inside a new outer packet with cryptography applied, site-to-site links routers permanently between locations, while remote access connects individual users to a gateway on demand. For protocols, remember the trade-offs. IPsec is mature but complex. SSL TLS plays nicely with firewalls, and WireGuard is the modern lean option. Split versus full tunnel comes down to whether internet traffic detours through corporate, and underneath it all sits the crypto stack. AES for bulk encryption, RSA for identity, Diffie-Hellman for key exchange, MAC for integrity, and perfect forward secrecy to protect past sessions. And here's your cheat sheet. Keep this one handy. Every term we've covered today is condensed into a single reference: the core definition of a VPN, the tunneling mechanic, the 2 deployment models, the three big protocols with their layer and port details, the split versus full tunnel decision, and even pre-shared keys as the simple but not scalable authentication option. When you're configuring a VPN in the wild and need a quick memory jog, this is the slide to screenshot. And that brings us to the end of Lesson 45, but the journey doesn't stop here. Next up in Lesson 46, we're going deep on IPsec. We'll unpack how IKE negotiates the keys, the real difference between ESP and AH, and when you'd reach for transport mode versus tunnel mode. If you've found this useful, head over to dargslan.com or the YouTube channel to keep building. I'll see you in the next one.